Welcome all to week 4 tutorial for the course Basic Linear Algebra taught by Professor Inder Kumar Rana. I am Pintu Kumar. I am a PhD scholar at IURIT Bombay. Today I plan to cover following topics: linear transformation, how do you convert a linear transformation to a matrix and vice versa, and rank nullity theorem for linear transformation. I'll be going through some of the questions related to these topics as well as some important theorems and their proofs. Okay. To begin with, let's see what is a linear transformation. Okay. So, given if you have U and V two vector spaces, a linear transformation is nothing but a function from the space U to V satisfying following two property. First, that if you take map of x plus y, they split, that is t of x is equal to t of x plus t of y. Second property is, if you multiply a vector x by a scalar c, then you can take that c out. This is called as homogeneity property. So any function that satisfies these two properties, that is t of x plus y is equal to t of x plus t of y, and t of cx is equal to c into t of x, for all x and y in your vector space U, then this kind of function is called as a linear transformation. Okay. So let's look at an example of a linear transformation and let's try to verify whether it's a linear transformation or not. Okay. So we are given a function from R2 to R2 defined by this. Now, t of a1 comma a2 is given as 2a1 plus a2 comma a1. Now, so we will try to first prove the first property of linear transformation, that is t of x plus y is equal to t of x plus t of y. Okay. So let's say we take x equal to x1 comma x2 and y is equal to y1 comma y2. Then let's try to evaluate the LHS first. Now t of x plus y is nothing but t of x1 x2 plus y1 y2, which is nothing but t of x1 plus y1 comma x2 plus y2. Now the first term over here serves as your a1 over here, and the second term over here serves as your a2 right here. So let's put that in this formula. What we will obtain is 2 times of x1 plus y1 plus a2, which is your x2 plus y2, comma a1, that is your x1 plus y1. If you simplify it a bit further, what you will obtain is 3x1, sorry, you will obtain something as 2x1 plus x2 plus 2y1 plus y2, comma x1 plus y1. Now, in order to verify, we also need to evaluate the right hand side. That is, we need to evaluate t of x plus t of y, and we'll check whether this quantity is equal to that or not. Okay. So let's see what's t of x1 comma x2 plus t of y1 comma y2. Now this term gives you 2x1 plus x2 comma x1 plus this term is 2y1 plus y2 comma y1. This is equivalent to 2x1 plus x2 plus 2y1 plus y2 comma x1 plus y1. If you see now, these two quantities are same. So we have proved the first property, right? Now we'll try to prove the second property in order to see whether this is a linear transformation or not. So let's see t of cx. Okay, what we would get? T of c of x1 comma y1, right? This is t of cx1 comma cy1. This is 2cx1 plus y1. So let's change this notation to x2. That would be better. It will match with the previous notation. Okay. Comma x1 cx2 plus cx1. Now if you take c common, you get 2x1 plus x2 comma x1. What does this give? C into t of x. So what we have verified is that t of c of x is equal to c into t of x. So we have verified this, that the given transformation is actually a linear transformation. Okay. Before moving forward, let's see an example which is not a linear transformation. Okay. Let's say we are defining a function from R to R, and t of x is given by x square. Now if you try to see t of x1 plus x2 is equal to x1 plus x2 whole square, which is x1 square plus x2 square plus 2x1 x2, which is not always equal to x1 square plus x2 square, which is indeed equal to t of x1 plus t of x2. So this can be treated as a counterexample or example which is not a linear transformation. Okay. Let's look at some of the properties of linear transformation. We'll try to prove them one by one. Okay. So the first property is that t of 0 is equal to 0. Okay, we'll try to prove this. So right now, remember that we have only two properties, that t of x plus y is equal to t of x plus t of y, and t of cx is equal to c into t of x. Okay, let's see what we can do over here. As you know, 0 plus 0 is always equal to 0. We can use something of this stuff. So on the left hand side, we split the inside 0 into two parts, which is t of 0 plus t of 0. And this is equal to t of 0. Okay. So what does this give? This gives us t of 0 is 2 times t of 0. What does this mean? This means that t of 0 is indeed 0. Okay. So any linear transformation will take 0 element to 0 element. This is the first property of a linear transformation. Now, if you look at some more property of linear transformation. So second property of a linear transformation says that if your t is linear, then t of cx plus y is equal to c into t of x plus t of y. This is quite simple, right? So you already know that t of x plus y is equal to t of x plus t of y. So if you break the LHS, so what it is equal to? This is equal to t of cx plus t of y, and you can take the c out. This gives you t of y. So this property was quite easy. Now again, if you look at this third property, so I'll just go through it briefly. T of x minus y, you can see it as t of x plus minus 1 into y. Now using the previous property, what you would get is t of x plus minus 1 into t of y, which is nothing but t of x minus t of y. Right. Again, this fourth property is also, so right now we have like written the definition of linear transformation, that t of x plus y is equal to t of x plus t of y. But this definition can be extended to like more than two vectors. So if you have something like this, you can split it again, t of x1 plus t of x2 and so on. You can, like, if you want to prove this, you can prove one by one. You can take first element as x and rest of them as y, and in the next step you can take this element as x and rest of them as y, and so on. You can proceed and prove this particular thing. Okay, we have a couple of questions related to linear transformation. Now, as I mentioned, linear transformation is nothing but a function. So I hope that you know what is a 1-1 function. If you don't, I'll just say what is a 1-1 function. F is called 1-1 if t of x is equal to t of y implies x is equal to y. If this property holds for all x and y belonging to the domain of f, then you call that a function as 1-1 function. Like in layman term, what do you mean by this is that every element is mapped to a unique element. So if two mappings are same, that is t of x is equal to t of y, then your x must be equal to y. Okay, this is what is called as a 1-1 function. So here we are given a linear transformation, and we are given that t of 1 comma 0 goes to 1 comma 4, t of 1 comma 1 goes to 2 comma 5, and then it has asked whether it is like what is t of 2 comma 3 and whether it is 1-1 or not. So regarding this 1-1 thing, we'll come towards it towards the end. We have a theorem that can say it is 1-1, but right now we'll calculate what is. We will calculate what is t of 2 comma 3. Okay. So we are given that t of 1 comma 0 is 1 comma 4 and t of 1 comma 1 is 2 comma 5, right? And we need to find the value of t of 2 comma 3. So what we will try to do is we will try to write 2 comma 3 in terms of these values 1 comma 0 and 1 comma 1. Okay, so if you see, how can we write 2 comma 3 in terms of 1 comma 0 plus something you need to multiply over here, comma 1 comma 1. One way you can see is that the second term is 1 more than the first term. So let's say if we multiply this thing by 3 and we multiply this thing by minus 1, what do we obtain? 3 minus 1 as 2 and 3 minus 0 as, so we can write it like this, right? So if we call this as vector v1, we call this as vector v2, and we call this as v3, then our v3 is nothing but 3 times v2 minus v1, right? I hope this is clear. Then what do we want to find? We want to find what is t of v3, which is equal to t of 3 v2 minus v1, which is again equal to 3 times t of v2 minus of t of v1. Now we know what is t of v1, t of v2, so just put it over here. This is 3 into 2, 5 minus 1, 4. Okay, we obtain 6 minus 1 as 5, 15 minus 4 as 11. So t of 2, 3 is 5, 11. Okay, we'll come to 1, 1 later, like almost towards the end of this class. Okay. So this is how you can find. Let's see one more example where we have to find a similar thing. Now what they are saying is, prove that there exists a linear transformation, okay, such that t of r2, r3 is such that 1, 1 goes to 1, 0, 2 and 2, 3 goes to 1, 1, minus 4. And again they have asked you to find what is t of 8, 11. Okay. So if you want to show existence of some quantity, if you can like build that linear transformation, if you can build that linear transformation, then that will surely show that that kind of linear transformation do exist, right? So if we show that for some linear transformation t of x, this t of 1, 1 is this and t of 2, 3 is this, then we can show. Now, whenever you want to write a closed form for a linear transformation, you try to find maps of standard basis. This is a very basic trick. So like if you look at R2, what is the standard basis for R2? Standard basis for your R2 is nothing but 1, 0 and 0, 1. Okay. So first of all, what we will try is, we will try to find map of 1, 0 and 0, 1. Okay. Let's name these things. Let 1, 1 be v1 and 2, 3 be v2. Okay. Now, how can we obtain 1, 0 from 1, 1 and 2, 3? Okay, we have to see this, right? So we want something to be multiplied here so that we get this to be 1, 0. So see that we want this quantity to be 1 more, right? So let's say if we multiply this thing by 2, then these things become, no, let's not multiply this thing by 2. Okay, we want 1, 0. So we want to multiply this by a, this by b, right? What does that mean? That a plus 2b is 1 and a plus 3b is 0. From here we can obtain a as minus 3b. If we put it in here, minus 3b plus 2b is equal to 1, or minus b is simply 1, which means b is your minus 1. Okay, so let's replace this b as minus 1, and your a is minus 3 times b, so this would be 3. Okay, So you can verify that 3 minus 2 is 1, 3 minus 3 is 0. Okay. Again, we want to write 0, comma 1. You guys tell me what should I write in place of a, comma b. I'll wait for you guys. I want to obtain 0, comma 1. So this gave me 3v1 minus v2. What should I write? You can write it in the chat box or you can unmute yourself to speak. So see, we want this term to be 1. We can just subtract minus 2 times of this so that this top one becomes 0 and let this be 1 only. So minus 2 plus 2 is 0. Minus 2 plus 3 is 1. Right. So what did we obtain here? We obtained that minus 2v1 plus v2. Okay. Now what we are trying to do is we'll use the property of linear transformation. So we want to find t of 1, comma 0. This is t of 3v1 minus v2, which is 3 times t of v1 minus of t of v2. Right. So this, what is t of v1? This is 102. So this is 3 times 102 minus 1 minus 1, 4. What do we obtain? This is 3 minus 1, 2. 0 plus 1 is 1. 6 minus 4 is 2. Again, we also need to find for t of 0, comma 1. Okay. So what is this? This is minus 2v1, t of minus 2v1 plus v2, which is minus 2 of tv1 plus v2. Right. So this is equal to minus 2 times 102 plus 1 minus 1, 4. What does this leaves us with? This leaves us with minus 1. This is minus 1. This is minus 2 plus 4 as 2. Okay. So why did we do this all? Right. So we were asked to prove that there exists such linear transformation such that this kind of thing holds. Right. Now we will try to write a general formula for this. Let's say we want to write a formula for t of x, comma y. Okay. We want to write this. How do we write this? Now you can see that t of x, comma y is nothing but x times 1, 0 plus y times 0, 1. Okay, and we have obtained these quantities. So what it is? X times t of 1, 0 plus y times t of 0, 1. This is x times 2, 1, 2 plus y times minus 1, minus 1, 2. So what do we obtain? T of x, comma y is equal to 2x minus y, comma x minus y, comma 2x plus 2y. Okay. And then this is 2x minus y. Yeah, x minus y and 2x plus 2y. Just a second. I think there is some calculation mistake here. So 3v1 6 minus 4 is 2. Yeah, so this is minus 4 plus 4, this term would be 0. Sorry for this mistake. So this is 0. This leads us to 2x. Okay. Yeah, now it is fine. So this is a general formula for linear transformation. And as you can see, every term is raised to the power just 1 and there is summation. So you can easily prove this to be a linear transformation. Okay. Now coming to, you can verify that this particular thing that you have obtained, like whatever you have obtained over here, this whatever you have obtained is satisfied by other points also, that 1 comma 1, if you put it in this, you will obtain this thing. If you put 2 comma 3, you will also. Now it has asked us to evaluate t of 8 comma 11. What is t of 8 comma 11? This would be 16 minus 11. This is 8 minus 11. This is 16. What do we obtain? This is 5 comma minus 3 comma 16. Is it clear to everyone? Like how do we obtain, like if we were given like two linearly independent points, that is v1 and v2, and we are given their maps. Then we retrieved the complete linear transformation, and with the help of that, we obtained the value at point 8 comma 11. Is it clear? I hope so. Okay. Now let's look at another example related to linear transformation. It is asking us to check if there exists a linear transformation such that t of 1 comma 0 comma 3 is 1 1, okay, and t of minus 2 comma 0 comma minus 6 is 2 1. Now if you look at this quantity, this whatever I'm highlighting in green is, like if you multiply that quantity by minus 2, you'll obtain what is on the right hand side. So if this is v1, if this is v2, then your v2 is minus 2 times of v1. We can see that. Okay. Now if this thing is satisfied, then your t of v2 must be equal to minus t of minus 2 of v1, right? So which is equal to minus 2 times t of v1. So what we had is that our t of v1 is 1 comma 1. Let's put it over here. We obtain minus 2 comma minus 2. But these quantity don't tally, right? So according to the given condition, our t of minus 2 v1 is not equal to minus 2 times t of v1. Hence, there can't be a linear transformation which satisfies these properties. So this is not possible. So the question was, is there a linear transformation? So answer is no, there is no linear transformation that can satisfy this thing. Okay. Okay. We'll see some important set of linear transformation. I hope the idea of linear transformation is clear to you. Just to just reiterate that linear transformation is nothing but a function from your vector space U to vector space V satisfying these two properties. First, that is t of x plus y is t of x plus t of y, and second, t of cx is c times t of x. Okay. Now in this question, we are given a special type of linear transformation. Actually, we were asked to prove whether it is a linear transformation or not, but we'll see how to do it. Okay. So what it is saying, that T of theta is a mapping from R2 to R2 such that if you have a point A1 comma A2, so this is a vector A1 comma A2, you rotate it by angle theta counterclockwise. Okay. So you have rotated this point counterclockwise to some point x comma y, and we want to see what is this x comma y. And for point 0 comma 0, you map 0 to always 0. This map is called rotation map by angle theta. Okay. Now, if you recall your geometry class probably, then for any vector, right, if it is a vector a1 comma a2, if you rotate it, then its length will remain constant, right? So if you are rotating, the length should not change. So if this point is a1 comma a2, then its length r is given by under root of a1 square plus a2 square, right? This is how you obtain the length of this thing. Okay. Now, if you know the r, you can use trigonometry to see what is its x component. Let's say if this is r length, okay, then what is this? This is angle beta that it is making with positive x-axis. Okay, then a1 can be given by r cos theta, because cos theta is base upon hypotenuse, right? So over here your base is your a1, so cos theta is a1 by h is your r, so a1 can be given by r cos theta. Similarly, your a2 can be given by r sin theta. So this a1, a2 get replaced by r cos theta, comma r sin theta. Now we are rotating this point, sorry, this is beta, not theta. Theta is the angle that I'm denoting between, after that is the angle of rotation. The angle that I chose over here is beta, not theta. Okay. Cos beta, this is sin beta, right? Now, for this new point x comma y, you can see that your x must be given by r of cos theta plus beta. So this angle is now a combined angle, right? And y is given by r of sine theta plus beta. If you use the trigonometry formula for cos of x plus y, what do you obtain? You obtained r cos theta cos beta minus r, sorry, r we have taken common, this is sine theta sine beta, and you obtain y as r cos theta sine beta plus r sine theta cos beta. Now if you look at one thing, that if you take r from here, okay, and you take cos beta from here, so r cos beta is nothing but your a1. So what is left in the first term? This is a1 cos theta. Again, in the second term, if you take r from here and sine beta from here, you get a2. So this is minus a2 sine theta. This is your x. And your, again, for the y, we'll also do the same thing. So we obtained r. This is r sine beta. R sine beta is nothing but a2. So this is a2 cos theta plus a1 sine theta. So what do we get out of this is, if you rotate, right, a vector a1 comma a2 by angle theta, so this is theta counterclockwise, then what do you obtain is a1 cos theta minus a2 sin theta, so a2 cos theta plus a1 sin theta. And you can verify that this is a linear transformation, right? You can verify this thing. Intuitively, if you want to see how it is a linear transformation, so let's say you first rotated it with angle theta 1, and then you rotated it again with angle theta 2, or you rotated, so what you have to prove is, in order to prove this as a linear transformation, that t of x plus y, or we should rewrite it as t of theta 1 plus theta 2 is t of theta 1 plus t of theta 2. So on the left hand side, what do we mean is that from starting from, let's say, so let's say we had a vector a1 comma a2, and we rotated it with some angle, this is theta 1 plus theta 2, or what could we have done is, we could have first rotated it by angle theta 1, let this be theta 1, and then again rotated it by theta 2, then we should obtain same vector. So your left hand side says that you have rotated it in one go from theta 1 to theta 2, and the right hand side says is first you rotated by angle theta 1, whatever you obtain, you rotate that thing, okay, by angle theta 2, okay. So this is same, right? This is what you will obtain. And again, for the like if you look at c times theta, then this would mean you are rotating theta 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 c times like separately, or what you can do is you can rotate c theta in one go, okay. So this rotation indeed is a like a linear transformation, and you can prove this. Another example is reflection about x-axis, okay. So let's say this is your x-axis, and you have some vector, right, given by a1 comma a2. If you reflect it around the x-axis, what would you would obtain is, let's say you obtain this thing. Now if you see, its x coordinate remains intact, right? So this is something like this. Just imagine that this is a straight line, right? So its x coordinate would remain intact. Now its length would, if the height is a1 a2 over here, then this would become minus a2, okay. So this is pretty simple one, that t of a1 comma a2 here is nothing but a1 comma minus of a2. This can also be easily verified as to be a linear transformation. The next one is something called as projection, which is also a linear transformation, okay. Projection you can see, okay. We'll move something to something called as null space and range space. You have already done this with respect to matrices, okay. So in a matrix, when you used to call a vector, so let's say you have matrix A, then null space of A was nothing but the set of vectors x such that Ax is equal to 0, right. Now for a linear transformation T, your null space of t is set of all vectors x such that t of x is 0. So all vectors which are getting mapped to 0 belongs to the null space of t. Okay. Null space is also called as the kernel of a linear transformation. This is same like two different names for the same thing. Okay. And the dimension of your null space is called as the nullity. Okay. Second thing is something called as a range space. Okay. So, like if you recall any function, how does a function look like? So, you will have some domain and you have some range. Okay. So, this get maps to this. So, this will get mapped to, let's say, this much portion of your space. Okay. It can be the case when all of your V is occupied, but it is not necessary that all of your V is occupied. So the portion of V that gets occupied in case of a linear transformation also forms a vector space. Okay. So whatever image space you get or the range that you get in the codomain, that is also a vector space, and that particular vector space is called as the image space or the range space. Okay. And the rank of this, sorry, the dimension of this range space is something called as rank of T. So in case of a matrix, you had a rank to be the number of non-zero rows. In case of transformation, you call the dimension of range space of T as rank of T. Later you will see that for every linear transformation T, you can find a corresponding matrix A. Okay. And that if you compare the nullity as well as the rank, these both the things will coincide for this transformation as well as for this matrix. Okay. So here is a formal definition. I was a bit crude, but here is a formal definition for what is called null space. So let V comma W be vector spaces and T is a linear transformation from V to W. We define null space or the kernel to be the set of all vectors x in V such that T of x is equal to 0. This is what I told you a few moments ago. Again, we define range or image of R2 to be the subset of W consisting of all image of T, all images of V under T. So if you take T of x, this set for all x in V, this is something as called as range space. Any doubt in definition of null space and range space of this linear transformation? If you have, you can type it or just unmute yourself and say. Okay. We'll look at an example and try to find the range space and null space of this. Okay. This is a simple example. Okay. So we are given with the transformation T of A1, A2, A3 is such that A1 minus A2, 2A3. Okay. First of all, let's try to find the null space of T. Okay. So what we want is, we want T of x to be 0. And we want to find, just a second, yeah. We want to find all such x which maps to 0, right? So let's say T of x1, x2, x3 is 0. Okay. So what is t of x1 comma x2 comma x3? By the given definition of linear transformation, this is x1 minus x2 comma 2 times x3. Okay. Now, if we look at how can we make a vector to be 0? If all of its elements are 0, then the vector would be called as a 0 vector, right? So if you want to make the first entry as 0, what would it give us? It would give us x1 is equal to x2 and 2x3 is equal to 0. This would mean x3 is 0. So what we can say about the null space now? So null space of T is given by vectors of form S, S, 0, where S is your any element belonging to field. So if you have first two elements to be same, then this is. Now let's also look at the dimension of null space of T. So by dimension we mean how many choices you have to fill in order to obtain a element of a null space. So for example, if you put in value of S over here, let's say you take S is equal to 1, then you will obtain something as 1 comma 1 comma 0. So you had only one choice to fill in over here, right? So the dimension of null space of T is 1. This is also called as nullity. Okay. Now, this was related to how to find the null space. Now we will try to find the range space of T. Okay. How do you find range space? So in order to find the range space of a transformation T, what you will try to do is, let's say your T is from, what is it written? Let's say it is from V to W. First step is you look at the standard basis for this. You can look at any basis, but standard basis would be easier for you. Then you take map of this standard basis, okay, and look at linearly independent elements out of them. That would give you the range space of T. The span of this linearly independent element would give you range space of T. Let's try to solve this. So our map is from R3 to R2. So standard basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So we want to find T of 1, 0, 0, want to find T of 0, 1, 0, we want to find T of 0, 0, 1, right? What is T of 1, comma 1, 0, 0? This is A1 minus A2, comma 2, A3. So this is 2 minus 0, comma 2 into 0, which is 2, comma 0. I'll just rewrite what is T of A1, A2, A3 over here. This is 2A1, right, sorry. A1 minus A2, comma 2A3, right? This is what it is, I hope. Yeah. So this is 2, comma 0. Again, if you look at this, this is minus 1, comma 0. This would be 0, comma 2. Okay. So once you have obtained value of this T of E1, E2, E3, you will try to look at the linearly independent vectors in the range space. Okay. So you can see that 2, comma 0 and 0, comma 2 are linearly independent, because no matter how you add them with some coefficient, this won't be able to make, so the first vector won't be able to add a 0 in the second term, and the second term won't be able to add a 0 in the first term, right? second vector won't be able to add a 0 in the first term. So these two are linearly independent, and by now you must be aware that R2 can have only two linearly independent vectors. So you can just simply ignore this one. Okay. So R of t is nothing but span of this is span of 2 comma 0 comma 0 comma 2, which is nothing but your complete R2. Now what is dimension of R2? Because you had two linearly independent vectors over here, dimension is 2. So null space of T was something of form s comma 0, and R of T came out to be span of 2 comma 0 comma 0 comma 2. Was it clear to everyone, please? If you will respond, then I'll be trying to help you better. If it is not clear, please you can either type in the chat box or you can unmute yourself. I'll wait for 2 minutes to see if it is clear or not. Okay, somebody asked what is the value of A1 and A2 in 100. Okay. See. So if you have a vector as 100, then your first element is A1, second element is A2, third element is A3, right? So it is same here, right? They had three elements written together. So you can either write it in this form or you can write it like this. This is same. Hope Ragul it is clear. So here my A1 was 1, A2 was 0, A3 was 0. That's why I made it oh, sorry.
How it is 2 minus
No, it
0?
is 1 minus 0. It would be 1, 0. Sorry for that. Right, and
Okay,
here
sir.
also it would be 1. Yeah. So this is the theorem that I just mentioned to you while solving the problem. So let's say you have a linear transformation from V to W. Okay. And beta is a basis for B, that is it contains V1, V2, V3. Then the range space of T is given by span of your, like if you take T of V1, T of V2, T of Vn, and you look at its span, that is your range space of T. So like if you want to write span of, you could have written span of 1, 0, and whatever second element we obtained, which was I think minus 1 comma 0, and then 0, 2, you could have written it this way also, but if you eliminate the linearly dependent vector, then you can easily look at the dimension also from there only. Okay. So yeah. Okay. Now I think I'll try to look at matrix representation of a linear transformation. Okay. So how do you, like few moments ago I mentioned that for every linear transformation you can find a matrix representation A. So for every linear transformation you can find a matrix A and vice versa, right? So we'll look how can we find. First thing that I want to mention is this matrix would depend on choice of your basis. So what does that mean? That your A won't be unique, right? So based on whatever A you choose, basis you choose, you will get different A's. Okay. So I think this is best done with the help of example. So I'll try to first write, I'll do it with an example only. So we have a transformation T from R2 to R2, which is given by T of x comma y is nothing but 2x plus 3y, comma 4x minus 5y. Okay, I'll try to do it in a step-by-step manner so that for those who don't know, they would be clear how to write a matrix representation. So I said you need to choose basis, right? Now how many bases you need to choose is one basis for your domain and one basis for your codomain. You need to choose. Now here we have same like vector space on both the side, so we can choose the standard basis over here. Let's first solve with the standard basis. So what is standard basis for R2? This is E1 is equal to 1 comma 0 and E2 is equal to 0 comma 1. This is a standard basis for E1 comma E2. So first step would be selection of basis for U comma V if your T is from U comma B. Okay. Now second step is find T of E1 and T of E2. So if you had let's say basis to be B is equal to beta 1, beta 2 and so on, then you will find T of beta 1, T of beta 2 and so on. So you find the images of your basis element. Okay. So what would be T of 1 comma 0? It is given by 2x plus 3y. So this is 2 plus 3 times 0 comma 4 minus 0. So this is 4, right? This is 2 comma 4. Okay. Now I'll do one step over here only. Whatever result you obtained, this is 2 comma 4, you need to write this in terms of basis element of your codomain. So right now we have this domain and codomain to be same. So it can be written as 2 into 1 comma 0 plus 4 into 0 comma 1. We will do this for the other one also. That is T of 0 comma 1. Now we again look at this. This is 3 comma minus 5, which is nothing but 3 times 1 comma 0 minus 5 times 0 comma 1. Now whatever information we have over here, we need to convert this into a metric. Okay. How would we obtain a matrix is, so for the first element of basis, whatever you obtained along with it some of the coefficients. So after you calculated this 2 comma 4, then you represented it in terms of summation of basis of your second vector space. You obtained some coefficients. You need to write this coefficient over here in form of a column. So the image of your first element becomes the first column of this matrix A. And again over here 3 comma minus 5. So this is the matrix that you have obtained for your transformation. T of x is equal to, this is 2x plus 3y comma 4x minus 5y. Okay, so for a linear transformation, you were able to find, like you were finding T of x. Now after you have obtained your matrix A, then your T of x is nothing but equal to A multiplied by x. So if you want to find the transformation of x, you just multiply A by x. Okay, this is what you need to do. So you can check it also that for any random x, so let's say this is 2, 3, 4 minus 5. If you multiply by x comma y, then it would be 2x plus 3y, and this is 4x minus 5y. So this was for a particular choice of your basis vectors. And also this x that you're taking should be represented as the same basis vector. So in terms of same basis vectors. So let's say if you want to find t of 2 comma 3, then because 2 of 2 comma 3 is equal to 2 times 1 comma 0 plus 4 times 0 comma 3 times 0 comma 1, that's why we will multiply it by the vector 2 comma 3. If we had selected some other basis that we'll see in the next example, then we would have multiplied it with some other vector over here. Okay. So any doubt on how do we represent a vector like this, or we'll have another basis, then it would be more clear. Okay, I'll first go for the second basis also, and then if there is some doubt, I'll address it. Okay. So the function is same, that is your t of x comma y is again 2x plus 3y comma 4x minus 5y. Okay, but now your basis has changed. Okay, so they are asking us to find the representation with respect to basis 1 comma 2 and 2 comma 5. Okay, so first step is again to find t of 1 comma 2. Okay, so what it would be? It would be 2 plus 3 to the 6, right? And the second element is 4 minus 10. This is 8 comma minus 6. So now, as we were doing before, we need to write this 8 comma minus 6 in terms of element of 1 comma, in terms of like sum of 1 comma 2. So this is, let's say this is 8. So what we want is that 8 comma minus 6 is equal to some a times 1 comma 2 plus some b times 2 comma 5. Okay. So how can we explain this? So your 8 is nothing but a plus 2b, or you can just replace a as 8 minus 2b, and your second one is that minus 6 is 2a plus 5b, which is now equal to 2 times 8 minus 2b plus 5b. This is minus 6. This would imply that minus 6 is equal to 16 plus b, or this would imply b is minus 22. And then what is your a? Am I actually doing it correct? Let's see. Then your a is 8 minus have I made some mistake here? 2x plus 3y. This is 1 comma 6. Yeah, this is correct. 1 2 plus 6 is correct here. So this is 4 minus 10. This is also correct here. Okay, let's see. This is 8 plus 44, which is 52. Let's see if this thing holds or not. Okay, so now what we wanted is, so let's say it's 52 times 1 comma 2 minus 22 2 comma 5. So this is 52 minus 44, and this is 104 minus, this is 0. Yeah, so this is 8 comma minus 6. This thing is holding, right? So what is the coefficients that we got now? The coefficients are pretty large over here, and they are, your a is 52 and b is minus 22, right? Similarly, now you can see that why we were choosing standard basis in the first place, because then your computations become very easy. Okay, so now this t of 2 comma 5, if you evaluate, what you would get is, this is 4 plus 15 comma 8 minus 25, right? So this is 19 comma minus 17. Now we need to write this 19 comma minus 17 in terms of some a comma 1 comma 2 plus b comma 2 comma 5. So what you would get is that your a plus 2b is 19, or a is 19 minus 2b, and again minus 17 is 2 times of a. So let's replace a straight away with 19 comma 2b plus 5b, right? So this would imply minus 17 is equal to 38 plus b, or your b is minus 17 minus 38, which is 5 minus 55. Okay, and your a then would turn out to be 19 plus 110, this is 129. So very large values over here. So we obtain this to be, this is 129. I hope all those calculations are correct. Even though it is, if there is some mistake in calculation, the approach that you are going to take is same. So now you have these coefficients with you, right? Here you had some, and now here also you have some. So your matrix A now, with respect to this specific set of bases, you can say S is given by 52 comma minus 22, right? And this is 129 comma minus 55. Okay, this was bit of calculation. And one thing that I want to mention is that it is not necessary that, like, let's say if it is a map from R2 to R2, then you take same basis on the both the side. You can take any basis of your choice on any side, but it is always recommended that you take a standard basis for easier calculation. Okay, and now if you want to evaluate t of x for some x, then you need to write x also in form of a of this, whatever this thing was, that is 1 2 2 5, 1 2 2 5. And then if you obtain a vector, let's say x tilde equal to a comma b after you have solved, then you can multiply this by vector a comma b to obtain t of x. Okay, now when we had standard basis, then it was quite easy. We could have directly used the same vector, because any x comma y is obviously x of e1 plus y of e2. Okay. Was it clear for everyone? I hope it was. Okay, Dheeraj. See, rank and eigenvector are two different topics. So eigenvector, I can give you the formula right now, but I'll be discussing it next week. Okay, these tutorials are 1 week behind the lecture series. So I can tell you how do you find rank of a matrix very quickly. So let's say if you have a matrix A, for example, let's say this is 1 2 and 2 3. First thing that you're going to do is you are going to do row reduce this matrix to echelon form. Okay, you can watch the recordings of previous video. There you will see how you can convert this to echelon form. So you want to make this entry to be 0. Okay, so if you make this entry to be 0, your matrix becomes 1, 0, 2 minus 1. How? Because I subtracted, I made R2 go to R2 minus 2 times R1. Okay. So after you have obtained your row echelon form, so the number of non-zero rows that you have in your row echelon form, so we have 2 non-zero rows over here, that is something that is called as a rank of your matrix. Okay. So how will you obtain is, first of all, you will row reduce your echelon form, and then you will count how many non-zero rows are there. That is your rank of a matrix. And for eigenvalue, how do you obtain is, I'll tell you, I'm not going into theory at all. So first, in order to obtain your eigenvector, then first thing that you need to find is something called eigenvalue. Okay. So if you have a matrix A, then lambda is an eigenvalue. Okay. Then it satisfies that determinant of A minus lambda I equal to 0. So let's say you have a matrix 1, 1, 0, 1. Then first of all, you will find A minus lambda I, that is I is identity matrix. So this would be 0, 1 minus lambda. Then you will find its determinant and equate it to be 0. So whatever values of lambda that you get, for example, over here you will get 1 minus lambda square is equal to 0, or this would mean that lambda is equal to 1 comma 1. So 1 is an eigenvalue for your this particular matrix, eigenvalue. Now, how do you go to eigenvectors from eigenvalue? Is vector v is eigenvector if it satisfies A minus lambda I into v is equal to 0. Okay, so you'll find a solution space for this, and that would be your vector space. So that vector space, you can pick any element and call it to be an eigenvector. I'll cover this thing in more detail next week. Okay. Getting back to what we were doing, so I'll solve one more example on matrix representation. Okay, and then we'll move to this rank nullity theorem. Okay, so we are given the space of function with basis this. Okay, so we are given S to be sine t, cos t, and e to the power 3t. Okay, and the map, that is your transformation, is defined as d of, or you can just write f dash of t. This is how it is defined. Okay, and we want to compute the matrix representation for this. Let's see how we can do. Now first step again would be to find transformation for elements of your basis, right? So d of sine t, what is d of sine t? It is nothing but cos t. Differentiation of sine t is cos t. So let's say we call this first one as v1, second one as v2, third one as v3. Then this is 0 times of sine t plus 1 time of cos t plus 0 time of e to the power 3t. So, okay, again we'll solve for the second one, that is d of cos t. This is minus sine t. This is minus 1 into sine t plus 0 into cos t plus 0 into e to the power 3t. Right. Now, if we look at e to the power 3t, this is nothing but 3 e to the power 3t, which is 0 sine t plus 0 cos t plus 3 e to the power 3t. So as I mentioned before, if you want to find the matrix representation, then the first column would be the coefficient of map of first basis element. So you would get as 0, 1, 0. In the second, you will get as minus 1, 0, 0. And the last column would be 0, 0, 3. This is the matrix representation for your differentiation operator if you take this as your basis. Okay. Now, one thing that you can see over here is, so as I mentioned, that t of x is equal to a of x. Okay. Now, if your a has dimension n cross m and x has some dimension p cross 1, right? So, as this x belongs to your, let's say this is a transformation from u to v, okay? So, the dimension of u would be p, right? Let's say your t is from R3 to R2. Then what would be the size of x? X would be also belong to 3 cross 1. X would also be a 3 cross 1 vector. So, this and this quantity should match for multiplication. So, the number of columns of A is nothing but dimension of your U. Okay. And what is number of rows? Now, if you look as number, I think I am, this is correct. Yes, this is correct. Now, what is number of rows? See, how many rows you would obtain is based on how many entries are here. Let's say you had only 2 entries over here, and let's say you forget about this thing. You forget about this thing. Okay. You had only 2 basis element over here. Then in every column there would have been only 2 elements, that is 0, 1 probably over here, right? So your number of rows of A is equal to dimension of V. Okay. So this is something we can keep in mind. I'll come back to this particular example if we have time left towards the end, but let's move to something called as rank nullity theorem. Okay. Any doubt in this? I think this example would have made it clear how do we find matrix representation of a transformation. If you have any doubt, I'll wait for 1 minute. You can type or unmute yourself. Okay.
Hello, sir.
Huh.
Sir, I have one query. If
Tell
I
me.
have I have lost my first 3 assignments, then may I eligible for to give exam or not?
Who is this? Who is speaking?
Dheeraj.
Dheeraj, see, I am not associated with course like exam and all thing. I am just
Okay,
here
sir.
for this tutorial
It-
sessions, right? So you
Okay, sir.
can,
Thank you.
I'll tell you what you can do. So there is a discussion forum for this course, right? You can
Okay,
ask
sir.
this question in the discussion forum, somebody might reply.
Okay, sir. Thank you.
Okay. Okay. So let's get to something called as rank nullity theorem. So for matrix, we have already seen rank nullity theorem. Okay. So as I mentioned, if you have a linear transformation, then you also have a corresponding matrix A. Now, one interesting thing is that your nullity of T, okay, and your rank of T would be same as your nullity of A or rank of A. Why is it so? Let's say we are looking at nullity. Nullity of T said that Tx is equal to 0. So all x such that T of x is equal to 0. If we now write it in form of matrix multiplication, what would it mean is that all x such that Ax is equal to 0. And this is nothing but how we define nullity of A for a matrix, right? So this is satisfied. Similarly, you can see what is rank of T. This is nothing but the image space of your matrix, that is T of x, right? Now, if you look at all A of x, right, then they can have as many as linearly independent vectors A of x as number of pivot elements of A. Now, the last thing that we had is that this was equal to number of for matrix, what it was, rank plus nullity. I think it was previous week. Yeah, just a second. I think it was number of columns. Yeah, number of columns of A. So rank plus nullity is equal to number of columns of A. Now, if you look at number of columns, we just said that that is equal to dimension of U. Or if you look at this example where your map is V to W, that is equal to dimension of V. So this is the same theorem, but we are stating it in different contexts. Okay. Okay. So this was just to mention like rank nullity theorem can also be used for your linear transformations. Let's try to prove some theorems. This might involve rank nullity theorem or might not involve rank nullity theorem, but are definitely related to your linear transformations. Okay. Now what it is saying is, let's say T is a linear transformation. Okay. Then we want to show that your T is 1, 1 if and only if your nullity of T is equal to 0. Sorry, null space of T is equal to 0. Okay. So it is an if and if only condition. So in order to prove this, we need to assume one and prove the other. And in the second step, we need to, so let's say if you have to prove, this is only for, let's say if somebody is from bachelor's, he might not know that if you need to prove that A if and only if B, then what you do is you assume A, then prove B in the first step. In the second step, you assume B and then prove A. This both combined gives that A if and only if B. Okay. So let's try this thing. So let's first assume let T is 1, 1. Okay, this we have assumed. Now what we have to prove? We need to prove that null space of T is 0. Okay, this is pretty easy, right? How we can do is, now we are given that T is 1, 1. And one thing we already know is that T of 0 is always 0. Okay. So let's try to look how a null space of T can look. So one thing that we are very sure is that 0 always belongs over here. Okay. Your 0 belongs to null space of T. Also, we are given that T is 1, 1. That is, there can't be two element x and y belonging to your vector space V such that your x and y are different and they map to same element. This is not possible. Okay. So what does this mean is there does not exist x not equal to 0 such that x belong to null of t, that is t of x can be 0. So there can be only one element that can go to 0, and we already know that 0 is already going to 0. So there can't be any other element that can go to 0. What does that mean? That means that nullity of t is equal to 0. One side is very easy to prove. Okay. One side is done. Okay. Now for the second side, we need to assume let n of t is equal to 0. Now we have to prove that t is 1, 1. So whenever you have to prove that a function is 1, 1, what you do is, let's say you have to prove f is 1, 1. What you do is you take f of x1 is equal to f of x2. Okay. What does this mean is that two elements are getting mapped to same point. If you take this and you end up proving that x1 is equal to x2, then you can then it is proved that your function f is 1, 1. So what does this mean? Let me reiterate. That is, if by any chance two things are getting mapped to same point, that is f1 f of x1 is equal to f of x2, then these 2 points must be same. If we are able to prove this thing, then we can prove that f is 1, 1. Okay. So let's try the same approach over here also. Let's take t of x1 is equal to t of x2. Okay. And our end goal is to show that x1 is equal to x2. Let's keep this in mind. This is our end goal. Okay. So our end goal is x1 equal to x2. Okay. So let's take this thing on left hand side. What does this give? T of x1 minus t of x2 is equal to 0. This means because t is a linear transformation, we can take this inside the bracket, is equal to 0. Now, as it is given to us that null of t is only 0, then the only thing that can go to 0 is 0. That means x1 minus x2 is 0. Or this means x1 is equal to x2. Hence proved. So we proved it to be 1, 1. So what is the takeaway from this? The takeaway that can you take is that if you have a linear transformation and if you want to check whether it is 1, 1 or not, then you just need to check null space of t. Okay, if null space of t is 0, right, then that function would be 1, 1. Okay. I hope this proof is clear. Okay. Okay, we'll come to this proof in a while. Let's first see this example. Okay. We are given that we have a linear transformation from polynomial up to degree 2 to polynomial up to degree 3, and the transformation is defined as such. We need to verify a rank nullity theorem for this. Okay. Now, first of all, we want to find the rank and the nullity. Okay. Let's start by so what is rank nullity theorem? The rank of t plus nullity of t is equal to your dimension of P2R. What is dimension of P2R? Dimension of P2R is nothing but 3. Right? What is the basis for P2R? Basis is 0, x, x. So this is not 0. It says 1, x, x square. and for your P3R it is 1 comma x square comma x cube. Okay, let's first try to find null space. So what we want is, we want all those functions which is 0. Okay, so this is one option to find nullity. Let's use rank nullity theorem to avoid looking at it, because this would involve solving. What would we have to solve? That 2 of f dash x plus 0 comma x of 3f of t is equal to 0. We need to solve this equation in order to find the null space of this particular transformation. But this doesn't at all seem trivial to me. In fact, I don't know how to solve this, right? So what we can try to do is, we will first try to find rank of t, okay, and then using rank nullity theorem, we can find the nullity out of it. Okay, in order to find rank, let's evaluate t of every element of basis. So let's say t of 1, this is 2 into f dash of 1, which is 0, plus 0 to x 3 into 1, this is 0, plus 0 to x, which is dt, 3 dt, this is 0 plus 3x, which is 3x. Okay, we obtain this thing. Similarly, we can obtain for x, this is 2 into 1, f dash x is 1, plus 0 to x, this is 3 t dt, this is 2 plus 2 plus 3t square by 2 from 0 to x, this is 2 plus 3x square by 2. Okay, now we have one more left, which is t of x square. This is now again 2 into x, this is 2 into 2x, which is f dash x plus 0 to x, 3 into t square dt. This you obtain as 4x plus, now the 0 term is not contributing anything. This is 3t cube by 3, which would mean t cube, or x t cube from 0 to x, which is again 4x plus x cube. So let's write it down clearly in terms of a vector. This is 3x, this is 2 plus 3x square by 2, and the last one we obtained is 4x plus x cube. Now, if you observe this thing, right, second term has x square in it, and none of the other terms has x square in it. Okay, so using this and this linear combination of first and second, it is not possible to obtain the second one, right? So this particular thing is your belong to linearly independent set. Okay, now if you look at this again, this has x cube, which is not possible from first two, then this is also correct. Now this one only has x in it, but now this don't have x in it. The third one has x in it. If you want to make this particular term as 0, or if you want to write as linear combination, then x cube term will also come into picture, but x cube is missing in the first term, right? So this particular term is also on the linearly independent set. So all these three vectors that we obtained are actually linearly independent. Okay, so what is rank of t? The rank of t is like how many linearly independent elements that you obtain after computing the image of a basis, right? So this is 3. Okay, so the rank you obtain as 3. Now using the rank nullity theorem, what is rank of t plus nullity of t is equal to dimension of v is equal to 3. So your rank is 3 plus nullity of T we don't know. This is equal to 3. This implies nullity of T is 0. Okay. So imagine if we had to solve this equation, which is obviously not possible, just to obtain that the only possible solution is 0. Okay, so this is very not at all great, but yeah, the rank nullity theorem can help us get the nullity value directly. Any doubt in this? Okay. I think I have an example also related to this. Yeah. Okay. I can delete it from. Yeah. So this is another important theorem. We can see this. Okay. What it is saying is, let's say you have a transformation from V to W, and this V and W have same dimension. Okay. For example, you have map from R2 to R2, or let's say you have a map from R3 to P to R, for that matter. That is, both the space, if they have same dimension, then these three things are equivalent. Okay. This is what we have to show. Now, if you want to show like three elements equivalent, then either you can go from 1 to 2, 2 to 3, or 3 to 1. What does this did is this completed a loop that you can move from anywhere to anywhere. Okay. So what I mean by going from 1 to 2 is that you assume this thing and then prove this thing. From 2 to 3 I mean that you assume the second thing and then prove the third thing. Or you can try to form loop in any way. So if you have three statements, you can form loop like this also. You can go from here to here and then here to here. Okay. This way also you can go from anywhere to anywhere, right? So there are a numerous way how you can prove three statement to be equivalent. Let's see what we can do over here. So we have A, B, and C, right? So now let's go from let's say A to C. Okay, let's try going from A to C. So let A be true. What do we mean if A is true? A is saying that T is 1, 1. Just now we did that if T is 1, 1, then nullity of T is 0, right? If my nullity of T is 0, then by rank nullity theorem, rank of T plus nullity of T is equal to dimension of V. Okay. So if A is true, this implies both these things. So this is if and only if, right? And this is if and only if. So this implies that because nullity of T is 0, because this is just a 0 element, so this implies that rank of T is equal to dimension of V. So we just proved that A if and only if C. So we have completed this loop. Okay. Now see what we can do. Because we know that rank of T is equal to dimension of V, and dimension of V is in fact equal to dimension of W. Now, if you have two space, let's say this is V and this is W, then V, if we are mapping, will get mapped to some subspace. Let's say this is the subspace to which it is getting mapped. Okay. Now, now if my rank is equal to the dimension itself, because see, the image space of T is a subset of your W. Okay. If now the rank of both these things become equal, in case of finite dimensional set, then both these sets actually become equal. Okay. So let's say that you have some subset of R2. Now if the rank of R2 S is also 2, then that is in fact R2 only, right? Then it will span the complete of R2. So because this rank of T is equal to dimension of W, then image space of T is nothing but W. So this map T that we have is in fact onto also. So using this B to C we went, and then we came from C to B. So you can see that you can reach from anywhere to anywhere now. So if you want to reach from B to A, you can go from B to C, then to A, and so on. So that's how we have proved these three statements to be equivalent. The proof might not be that like interesting or appealing, but its applications are many. So if you have any linear transformation such that their dimension, that V and W dimension are same, then proving one of them can lead to you to the other two. We'll see with the help of examples. Okay, so let's try to do true false, then yeah, we can do this last one also. Okay. Okay. We left a question in the beginning. Let's come back to that question. Okay. For those who joined late, here we had a question that let's say that T of 0, 1 is 1, 4 and T of 1 is 2, 5, right? Then what is T of 2, 3? And if this is 1, 1, okay. Now we showed that that we obtain like this T of 2, 3, right? Now, if we treat this 1, 0 and 1, 1 as a basis, right? We can treat because this 1, 0 and 1, 1 are linearly independent. Then you can see their maps are also linearly independent to each other. This is no way you can, these are a product of each other, right? So, its rank of T we obtain to be 2, right? Now, if you remember the last theorem that we did, if we have mapping from V to W, such that dimension of V is dimension of W, here you can see that both the dimension are 2 only. Okay. Then, because the rank is 2, this is an onto map, right? Because the right hand side is 2-dimensional and rank of T is also 2. Then this is an onto map. Now, because it is an onto map, you can clearly say that it is a 1-to-1 map also. So this is correct. Another way to look at it is, if you don't want to get into that theorem, is that rank of T was 2. Now using rank nullity theorem, we can go rank of T plus nullity of T is equal to dimension of this first space, which is equal to 2. Now rank is already 2. This space we don't know. This is 2. So what is this? This is 0. Now if my nullity of T is 0, null space is just 0, then again we know that it is a 1-to-1 map. Okay. Okay, let's do true and false, and then we can close this session. Yeah. I think there are few people here. It would be great. Ravi Shankar, can you please elaborate what you are not able to access? So this problem solving session, these videos you are not able to access. This is what you are saying. Okay. Thank you, Ravi. Okay. So if you guys will reply to this true false answer, then probably it would be more beneficial for you. So let's see. So we have to mark every statement as true or false. Okay. So we have T from V to W. Okay. And there is nothing given about whether they are same dimensional or not. So that is not to assume. The only thing is that they are finite dimension. Anything that you will come across in this course will always be finite dimensional. So you need not worry about that. Okay. So first thing is, if T is a linear map, then it preserves sum and scalar product, whether it is true or false. So what it is saying is, preserve sums mean that T of x of y is T of x plus T of y, right? And if it preserves scalar product, this means T of Cx is equal to C times T of x. So whether it's true or false, you can type in the chat box, whoever is there. If T is a linear map, does a linear map satisfy these two properties, right? This is true. This is the definition of a linear transformation, right? Second one is, let's say if this property is satisfied, that is T of x plus y is equal to T of x plus T of y. Is it necessary that my map would be a linear map? No, right? We need another property also, that T of Cx is equal to C times T of x. So this is false, right? Okay, the first two are quite easy. Let's go to the third one. I think the font size is adequate enough for you, or I'll just make it a bit large. Wait. This is C. P is 1 to 1 if and only if the only vector x such that T of x is equal to 0. Now, one thing that you should keep in mind is that we are given T is a function. We are not given that T is a linear transformation. We are given that T is a function, not a linear transformation. If T was a linear transformation, then this is the theorem that we prove, that T is 1 to 1 if and only if nullity of T is equal to 0. That is, the only vector that T of x is equal to 0 is 0. But is it true for any general function? Like if T is not a linear transformation and T is any arbitrary function, then is it necessary that if my T of x is equal to 0 is satisfied only for x is equal to 0, then T is 1, 1. Is it necessary? We can take an example, right? Take f of x is equal to x square. Is x square a 1, 1 function? If you draw this curve, so for every y you
No,
have
sir.
2 points, right? Yeah. So if you take f of x is equal to x square, then it is 0 only at x is equal to 0, but it is not a 1, 1 function. So this property is satisfied only for linear transformation. This is simple. Let's skip to this question.
So, sir, C is true, sir.
C is false. See, agar ye, if this T would have been a linear transformation, then this was true. But right now we are given that T is any arbitrary function. Then it is false. Okay. Then we have D part, that T of 0 is 0. This is pretty obvious. We already know this thing. Next one we can solve E1, that if T is linear, then nullity of T plus rank of T is equal to dimension of W. Is this true? What does the rank nullity theorem say? It says that nullity plus rank is equal to dimension of V, not W. So this one is also false. Okay, so if T is linear, then T carries linearly independent subset of V onto linearly independent subset of W. This is also false. If you take T of x is equal to 0, then every element is carried to 0, and this set is not at all a linearly independent set. This is a linearly dependent set because it has only 0 in it. So this is also false. Last part is, if T is a map from V to W, are both linear and agree on the basis for V. Yeah, like what it is saying is, we have some basis B is equal to beta 1 comma beta 2, right? Let's say there are two elements only right now, and T of beta 1 is equal to U of beta 1, and T of beta 2 is also equal to U of beta 2. Then it is asking whether T is equal to U or not. And T and U are both linear transformations. Yes, if they agree on basis, then they'll definitely agree on other points also. Yeah. So this is what I planned. I had some more examples, but I don't think that would be covered in this particular time. You can see this, I'll upload this, you can access these things. And yeah, most of the examples that I have picked is from Friedberg's book. So if you are interested, you can uh, read that book. I definitely suggest reading book.